In the last video, we introduced the binomial distribution. We looked at the conditions for a binomial experiment, and then we looked at the formula for probabilities about binomial random variables, or the binomial probability distribution function, and we looked at how to find the expected value and variance for a binomial random variable. Right, in this video, what we're going to do is actually put that stuff into practice. All right, so we've got a little problem here, and we are going to work through this. All right, so what we have here, I'll just go ahead and read this out. So a device used to check oxygenation levels has 5 sensors. The probability that a sensor will fail is 0.27. Create the probability distribution for sensor failures. All right, so that's where we're starting off. There's a couple of key pieces of information we want to check for. Right, if we look at that formula, that distribution function, we know that there are 3 things that we're going to need to know. We're going to need to know the number of trials. We're going to need to know the number of successes for a particular probability, and we're going to need to know the probability of a success. All right, we're going to get 2 of those 3 things from a problem like this, all right, by actually looking in the body of the problem. The other one, right, we're going to have to get from what's actually being asked. All right, so the things that we're going to need to pull out of this problem are N, so the number of trials, and P, for the probability of success. So when we're looking for the number of trials, right, one, we just kind of read this and look and say, well, what are we looking at, right? What are we doing multiple times, right? And what we're doing multiple times is looking at a sensor, right? There are 5 sensors. That's what this problem is about. We're talking about the probability a sensor will fail. So really our trial is looking to see whether or not a sensor fails. And we have 5 sensors, so we have 5 trials. So N is going to be 5. All right, so we have 5 sensors. The next thing that we're going to need to pull from this problem at the top is the probability of a success. All right, well, we've got a probability statement right here. All right, the probability that a sensor will fail is 0.27. All right, so 1, that's going to indicate what our successes are. Right, whatever the probability you're being given, right, that's usually going to be the probability of a success, and so that's also going to tell you what a success is. In this case, we're given the probability that a sensor fails, so our success is a sensor failure. Right, so again, remember that what we call a success does not have to be something positive, right? So we could flip it around so that a success is a perfectly functioning sensor, right? But in this case, right, especially when we're starting off, we probably want to just take what's in the problem as a success, right? You can flip it around, but you're going to have to change a lot of stuff, and it's more confusing and more complicated than it's probably worth at this stage, right? So just whatever probability you're going to only be given one probability in like the main body of the problem, right? Whatever that is P, right? In some cases you'll have to find it on your own, but you will be told, all right, enough information to find it. All right, but so since the success is a sensor failure and the probability a sensor will fail is 0.27, right, that means that P, our probability of success, is 0.27. All right, so those are the 2 pieces that we can get from this problem. All right, the last thing that we need is X, but that's going to come from what probability we're actually calculating. All right, so let's go ahead and start actually calculating some probabilities. The last thing, so it says create the probability distribution for sensor failures. So essentially what this is asking us is to find, right, we want to create a probability distribution. Right? We want to describe this random variable, right, or this process, this random process. And so we're going to follow the same steps that we did previously in this chapter for describing a discrete random variable. All right, we're going to state our, well, we've really already stated our variable. It's number of sensor failures. All right, then we're going to list all of our possible outcomes, and then we're going to find those probabilities. All right, so that is what we're going to start doing. All right, we know that our variable x equals number of sensor failures. All right, now we need to list our possible outcomes. I'm going to do it over here. All right, so when we go to list our possible outcomes, we need to think, all right, well, what are the possible outcomes, right? We have 5 sensors, right? So it's possible that 1 through 5 can fail, right? So we can have 1 failure, we can have all the way up to 5 failures, right? So 5 is going to be our maximum, right? As for our minimum, right, we think, well, maybe it's 1. However, is it possible to have fewer than 1 failure? Right, and the answer is yes, right? We could have 0 failures, right? So on this, we're going to need to have 0 to n, all right? Whatever the number of trials are, right, it's going to be 0 to n. Those are going to be all of the possible outcomes. So 0, 1, 2, 3, 4, and 5, all right? Those are all of our possible outcomes. All right, now we need to find the probabilities, all right? We're going to find those probabilities with the binomial probability distribution function. All right, if we don't remember what that looks like, we'll see if I can fit it in here. All right, that is it. All right, so NCX times p to the x times 1 minus p to the n minus x. All right, once again, this is simply saying, right, how many ways can this occur? Right, here we have the probability of a success raised to the number of successes, right, times the probability of a failure raised to the number of failures. All right. So let's go ahead and actually do one of these. All right, so we're going to do just the first one. Let's say probability x equals 0. All right. At this point, right, once we actually have decided which probability we're going to calculate, all right, the rest of it is just kind of filling in. All right, so we know that n is 5, so we're going to have 5c0. All right, we're going to multiply that by the probability of a success, which we know is 0.27, raised to the number of successes, right, or x. Here, x equals 0, so we're going to raise it to the 0th power. And then finally, we're going to multiply it by the probability of a failure, right? So you could put it in as 1 minus 0.27, but I'll say that I found it to be much easier to simply do the 1 minus 0.7 and say, 1 minus p actually equals, and then do that calculation off to the side. So 1 minus p, or 1 minus 0.27, that's going to give us 0.73, right? And then n minus x, in this case, n is 5, x is 0. So, right, 5 minus 0 gives us 5. All right, so that's what we need to put here in our exponent. All right, so once we've set it up, right, we can then, all right, actually put this into our calculator. All right, so remember that this 5C0, right? This is the combinations function, right? If you have a scientific calculator, and you should for this course, right, then you are going to find this function somewhere, right? I think I mentioned this in the last video, but if you have a kind of a basic, or a general Texas Instruments scientific calculator, you're going to have a little PRB button kind of up towards this part of it. I don't even know if y'all can see that. That might be too far away. But up near the second button, if you have a Casio scientific calculator, it's going to be a secondary function of kind of around the numbers. All right, it might be to the kind of upper right of where the numbers are, right? But it's going to be a secondary function in there, and it's probably going to look like NCR or something like that. All right. If you have a graphing calculator, it's probably going to be somewhere in a menu, and depending on which one, it's going to depend on where that menu is found. So if you can't find it, you can almost certainly just Google that and find somebody telling people where those are. Right. But that's how we're going to punch that in. So usually on these, you need to put in your n, so 5, and then however you get to that combinations function, you get to it and hit enter, and then you put in your x, so then you would put in 0. Right? Another thing is if you do this all at once, you need to put brackets, right? I would suggest putting brackets around all of these terms, all right? So one around the combination, one around the p to the x, and one around the 1 minus p to the n minus x. All right, but after all of that, right, once we've gotten it into our calculator, once we've hit enter, we should find that the probability is 0.207. Right, and so we could just fill that in. Right, I want to talk a little bit more about this. So the x equals 0 and x equals n, which in this case is 5. You can kind of take a shortcut if you want, because when we are looking at what we're actually doing, and we're doing these all individually, right? The combinations function here, 5C0, this is asking, right, how many ways could we have 0 failures out of 5 sensors, right? And the answer to that is 1. There's only one way for that to happen, right? All 5 sensors have to fail. There's no other way for that to occur, right? So if you're doing, NC0, all right, so whatever your number of trials are, C0, or NCN, which in this case would be 5C5, right? That's always going to equal 1, right? Because if you're going for 0, then there's only one way. There are no failures, right? I think I said it the opposite way earlier, right? If it's 0, 0 is a failure. So if x is 0, then there are no failures. The only way for all of them, none of them to fail, there's only one way. They all have to, none of them can fail, right? And then the flip side is true for 5, right? If all 5 of the sensors fail, well, there's only one way for that to happen, all right? Then, right here, when we go to the next part, right, the p to the x, right? Well, we're raising it to the 0th power, and anything raised to the 0th power equals 1. All right, so when you're doing the x equals 0, it's going to be the first one that's going to be raised to the 0th. If you're doing, in this case, 5, or just whatever your n is, right, this, you'll have that 0, right, you'll have 1 minus p to the 0. All right, and so that's going to equal 1. All right, well, all that leaves is 0.73 raised to the 5th. All right, if you just put 0.73 raised to the 5th into your calculator, right, you're going to get 2.07, right, which makes sense because obviously that has to be true, right, if that is what we get from punching the whole thing in. All right, because 1 times 1, right, times whatever is just going to leave us with that value. All right, but that is, again, kind of a shortcut. So if you're doing x equals 0, you can just raise 1 minus p to the number of trials, right? And that's going to give you the answer. Right? If you're doing probability x equals 5, you can just raise the probability of a failure, probability of a success to whatever n is. All right? All the ones in between, you actually do need to put this information in. All right? But that's a shortcut. If we remember, that can make things a little bit easier. But also, if it's just going to confuse us, we probably want to just ignore it. All right, but so that is x equals 0. All right. Now let's move on to the next one, and we'll set up a couple more of these, and then I'll probably just fill this in, and we'll talk about some other things. All right. So let's do probability x equals 1, just so we can continue moving along. All right. So NCX. All right. N is still 5, so 5C, and then x. Now x equals 1. All right, we can look at our probability statement and see x equals 1. All right, then we'll multiply it by the probability of a success, 0.27. Raised to the number of successes, that's 1. Times 1 minus p, all right, which we already know is 0.73, raised to n minus x. N is 5, x is 1, so 5 minus 1 gives us 4. All right, so once again, we're just going to punch all of this into our calculator, and we are going to get 0.383. All right, and so we would just fill that in over here. Again, we would just continue to do this. Really, all we're doing every time that we're doing one of these, we're just going in, we're really just changing the x, right? Once we've got it set up for the initial kind of run, all right, the only thing that's going to change is the x, all right? N is going to stay the same. You can't change the number of trials halfway through anything, all right? We already know that p does not change from trial to trial. It's constant. That is the value, all right? So that's not going to change, right? And then, obviously, 1 minus p. Since p is a constant, 1 minus p is also going to be a constant. All right, so then we're only changing these x's. So that's the only thing that we're really having to go in and change. All right, so for the probability x equals 2, we would have 5c 2 now instead of 1 times 0.27 squared times 0.73 to the third. All right, and that would give us 0.284. All right, so that is how we are going to use this binomial probability distribution function. I'm going to go ahead and fill in the rest of these real quick. So the probability x equals 3, right, is 0.105. The probability x equals 4 is 0.019, and the probability that x equals 5, right, so the probability that all the sensors fail is 0.001. Right, a lot of times it's very helpful to write out the entire distribution, right? Obviously, if I ask you to write out the entire distribution, that's what you should do, although I kind of doubt I'll do that on the online classes, because that would be difficult to put into one of those online tests, right? But if you're not asked to do it, you don't have to, right? However, in some cases, it can be a good idea to go ahead and write it out, right? If you look at the problems you're going to have to answer for a particular scenario, if you're going to have to calculate all of those probabilities anyway, right, you might want to just go ahead and do the distribution, right? That way, when you go to actually answer the questions, you can just pull what you need, right? Instead of having to stop and calculate stuff in the midst of that, all right? That tip really is more pertinent for face-to-face courses, right? But it may or may not be helpful for online, all right? most of the time, but most of the time I'm not going to just ask you to give me that distribution. Right? A lot of times I'll just ask you questions, right? We're going to do that in just a second. Before we do that, though, there is one other thing I want to do before we look at that last thing. All right. One thing that I wanted to mention is looking at our probabilities, right? We know that for a probability distribution, the probability should add up to 1, right? Well, if we add up if we add up these probabilities, right, they're not going to add up to 1, right? Which I'm very glad that they don't, because this kind of illustrates something I said in a previous video, right? If you're calculating these yourself, right, and I calculated these, and just like you would, right? Especially when we get into these binomial and the next thing to come, right? Because of the way the formulas are working, right? And when we start rounding, right? There's a chance that we get something like this, right? Where we get 0.999 or 1.001, right? And that's okay, right? If you're 1/1000th off, right, that's going to be fine, all right? Again, especially when you are the one calculating it, especially when we have something like the binomial, all right? So I wanted to point that out. All right, the next thing I want us to talk about is, let's quickly do an expected value problem. All right, so we know that for a binomial random variable, the expected value is equal to n times p. All right, so for this, 5 times 0.27. All right, and we're going to find that the value we get is 1.35. All right, so one, that's just how we would do that. So just an example of how we would do that. All right, but one thing I would like to note is that 1.35, all right, if we look at where it would fall in our distribution, all right, it would be somewhere like here, right? So this would be our 1.35, right? It's closer to the 1, right, than the 2, but it is in between them, right? And if we look at the probabilities, right, on either side of that blue line, we can see that that's where the highest probabilities are, right? Which makes sense, right? We would expect, right, a higher probability of values around the expected value, right? Because it's the expected value. It's what you would kind of expect over multiple iterations that you would kind of come to, right? And so it makes sense that the probabilities, right, for the values around that expected value are the highest. All right, we can also go ahead and look at our variance, all right, which we know is n times p times 1 minus p. All right, so n is 5, p is still 0.27, and 1 minus p is still 0.73. All right, so when we do that, all right, we're going to get a variance of, just lost, 0.9855. All right, so that is our variance. And if we took the square root of this, all right, to get our standard deviation, we would get essentially, since it's pretty close to 1, it's essentially just going to be 1. All right, but we're going to get a slightly higher number, 0.993, we'll say. All right, I'll write that up over here just in case anybody's. All right, and then if we kind of look, right, 1 away from that 1.3, all right, so that would be 0.3 to 0.35 to 2.35, so that's just one standard deviation away from the expected value. All right, we're just going to say 1 away because that's close enough and that's going to be easier. All right, we can see that that range, right, which we could probably just essentially say goes from here to here. All right, we can also see that that's where the higher probabilities are as well. Right, and if our standard deviation was higher than 1, right, it would kind of keep going out and we would still have higher probabilities kind of farther out away from the mean, right? And then we would see sharp drop-offs after that, right? But that is just something that I wanted to point out about kind of how these work. All right, so with that said, all right, now that we've got our expected value and variance out of the way, let's talk a little bit about kind of answering questions about these. All right, so really all we would do, right, most of the time I would ask you something like, what's the probability that, you know, I might give you a simple one, say, what's the probability that no sensors fail? All right, in that case, you would say, all right, well, if no sensors fail, then we have 0 sensor failures. So x equals 0, right? The probability that x equals 0 is 0.207, all right? We just grab it right off the table. All right, but I might ask you something like, what is the probability at least 3 fail? All right, so what is the probability that at least 3 of these sensors fail? All right, well, we would want to go ahead and set up a probability statement. So at least 3, all right, so that's saying that 3 is the minimum, all right? So 3 is kind of the bare minimum. Anything above that is fine, but anything below it is not. All right, so the probability x is greater than or equal to 3, all right? So at least 3, so we're including 3 and everything above it. All right, well, to find this probability, all right, we just need to add up, right? Remember that our discrete probabilities are additive. All right, so to find the probability x greater than or equal to 3, all right, we're going to need to add the probability x equals 3 plus x equals 4 plus x equals 5. So 0.105 plus 0.019 plus 0.001, right? And that is going to leave us with the probability x greater than or equal to 2 is equal to 0.125. That is bad. All right, so 0.125, unless I did that math in my head wrong. All right, that is more or less the main way that these are going to be asked, right? And so if we were to be asked this first and we weren't asked to do this distribution, right, we could have just found the probability that x equals 3, 4, and 5, right, added those together without doing the other ones, all right? But again, if you're going to be doing multiple problems based on the same scenario, which you will, you might end up having to find them all anyways, right? And so it can be helpful to just go ahead and do all of those calculations right in a row, so that way when you get to the question part, you don't have to kind of stop, all right, say, well, okay, here's the probability statement, here are the probabilities I need, now I have to go calculate them. All right, you can just grab them from the table and kind of not break your stride, as it were. All right, but again, that is essentially what we're doing. That is how we're going to do kind of all of these. Yeah, I mean, that's basically it, right? That's binomial probabilities. That's how we calculate the individual probabilities, right? When we get to the kind of more complex ones, I guess you could say, right? All we're really doing is just adding those individual ones, all right? That's all we're going to be doing here, all right? But that is it for this video, all right? And it for binomial distributions. In the next video, we will be introducing the concept of the Poisson distribution. So another special case of a discrete probability distribution. This one probably is a little bit simpler, so we probably can get that one done in one video, but I do like to talk, so we'll see. All right, but regardless of all of that, that's it for this video, and I'll see you in the next one.